Hi, welcome to the next topic of nuclear chemistry, that is consecutive decay and radioactive equilibrium and neutron activation analysis. These are two topics we are going to discuss: consecutive decay and radioactive equilibrium and neutron activation analysis in this part of the lecture. What do you mean by consecutive decays and radioactive equilibrium? If a radioactive disintegration takes place in n different stages, then they are called consecutive decays. If the decay products are radioactive themselves, it leads to an interesting situation. That is, radioactive pulse comes into radioactive equilibrium after some time. For example, if we take this series, this one, radium undergo disintegration and is converted to radon, that also radioactive. Then it is disintegrated to radium A, it is A, and it's converted to radium B. For example, radium for instance changes to radon, and changes to radium, then changes to radium B, and so on. Then, if you take this radium in a vessel, that is a vessel initially contained radium only, but after some time, it undergo disintegrations, and the vessel containing radon is there, radium A is there, radium B is there, and etc. It's gone. And the first, initially the quantity of radon will increase rapidly, but since its rate of disintegration also high, a stage at we reach that is known as equilibrium, that is the number of atoms of radon formed per second will equal to the number of atoms of radon which disintegrates per second. Is number of atoms one formed is equal to the number of atoms of, and other one disintegrates per second, giving rise to the radium A. At this stage, the concentration of radon will remain unchanged. The radon is then said to be radioactive equilibrium with the given amount of radium, and that is known as the radioactive equilibrium. In the same way, radium A and radium B will also reach a state of radioactive equilibrium with the preceding member of the series. And so, first one is equilibrium with the second one, and second one is equilibrium with the third one, and that is known as the radioactive equilibrium. If we derive, if we take Na, Nb, Nz, etc., the number of atoms of the various parent and daughter element. First one is known as parent element, which is integrated to the daughter atoms, and lambda 1, lambda 2, lambda 3, etc. are there, disintegration constants respectively. Then lambda 1 into Na is equal to lambda 2 into Np is equal to lambda 3 into Nc, etc. is equal to a constant. And lambda is inversely proportional to T half. And the equation becomes Na by T half A is equal to Nb by T half B is equal to Nc by T half C is equal to a constant. 693, that is a constant. So at any instant, Na into lambda 1 is equal to Nb into lambda 1. That is equilibrium with respect to the parent in preceding element, and that is known as radioactive equilibrium. Then there are two states are there, that is transient and secular equilibrium. Transient and secular equilibrium. Depending on the half-life period of the daughter nuclei, two general cases arise. That is, if the parent half-life is greater than that of the daughter, a steady state is called a transient equilibrium is reached. If parent radioactivity is longer lived than daughter and the activity of the parent does not fall measurably during many daughter half-life, and that steady state is known as secular equilibrium, and the secular equilibrium is limited case of transient equilibrium. The main difference between two equilibrium is given by, that is, one is average half-life tau 1 is very much greater than tau 2, and that condition is known as secular equilibrium, and transient, that is tau 1 is greater than tau 2. That is, tau 1 is the average half-life period of the element. For it takes tau 1 is very much greater than the observation time. Tau 1 is 10 to infinity and lambda 1 become equal to 0, e raised to minus lambda t 1. The general equation becomes n2 is equal to lambda 1 by lambda 2 minus lambda 1 n1 e raised to minus lambda 1 t minus e raised to minus lambda 2, which simplify n2 is equal to lambda 1 by lambda 2 is equal to n1 into 1 minus e raised to minus lambda 2 t. So that is the case of secular equilibrium. But in the case of this one, transient equilibrium, the general equation remain unchanged. After sufficiently long time, that's n2 become lambda 1 n1 by lambda 2, or n2 by n1 is equal to lambda 1 by lambda 2. But in transient, that is n2 by n1 is equal to lambda 1 divided by lambda 2 minus lambda 1. That's the difference between this transient and the circular equilibrium. Take the case of is on strontium, that is 90 and is 28.1 half-life period and 64.1, but it's in the case of barium that is 12.8 days and 14 hours. That's the condition for this transient and the secular equilibrium. Next is neutron activation analysis, another topic related to this nuclear chemistry. It is neutron activation analysis. In neutron activation, what is neutron activation analysis? A process for determining the concentration of elements present in a material. Relies on the excitation of by neutrons so that the treated sample emits gamma rays. This is based on the neutron gamma reaction. It allows precise identification and quantification of the elements, above all the trace elements in the sample. It is neutron active application in chemistry, but also in other research areas in geology, archaeology, medicine, environmental monitoring. In forensic sciences, we can use this neutron activation analysis to find the concentration of elements in a particular material. It is a non-destructive analytical method commonly used to determine the identify the concentration of the element. Unlike any other analytical technique, NA is based on the nuclear rather than the electronic transition. For example, this one, P31 undergo bombardment with the neutron P32 plus gamma emit the gamma ray, or cobalt 59 plus N0 neutron is cobalt 60 plus gamma radiation. So a schematic for the uh, basic mechanism for a neutron activation analysis. That is, N is a neutron that hit the target molecule, that is cobalt 50. Neutron capture occur, that is excited nucleus takes place. It is cobalt a metastable or it's undergo excited nucleus. Then it emits gamma radiation, or it undergo internal transformation, that is radioactive cobalt 60, and it's undergo radioactive decay, that is emit beta uh, nickel 16, it's emit excited nucleus, or it's emit gamma radiation, and in order to transform it's converted to nickel 60. It's a stable molecule. From this one we can able to analyze the material from this gamma emission of this one. It's a method for element determination based on the measurement of characteristics gamma energies from artificially producing radionuclide. By analyzing the or measuring the gamma radiations, we can able to analyze the concentration of the material. This radionuclide are formed by bombarding stable elements with the neutron. Is performed using a nuclear reactor that produces thermal neutrons. When stable elements are irradiated with the thermal neutrons in a reactor, the elements become radioactive due to the neutron capture of the core. Radioactive nuclei in the sample undergo both gamma and particle nuclear decay. That's figure above present schematic example for the nuclear decay. After capturing free neutron, the excited cobalt 60 M nuclei undergo an internal transformation by emitting gamma rays. The lower energy doctor cobalt 60, which is still radioactive, then emits a beta particle. This results in high energy nickel 60 nucleus, which once again undergo an internal transformation by emitting gamma rays. The nucleus then reaches a stable Ni60 state. In that way, we can able to analyze the concentration of a particular material, and that is known as neutron activation analysis. And how you can determine the concentration by radiation, radioactive, and measure the conventional radiochemical methods. That is, a certain amount of radiated material is measured over a certain time, depending on the amount of radioactive material in the sample. Instrument like ground and blank samples measured in advance, and energy calibration and efficiency calibration of the respective geometries are added. So we can determine the disintegration measured in becquerel is unit quantitative determination, that is dt is equal to sigma phi nd into 1 minus e raised to minus lambda t, where nd is the number of stable nucleides that are irradiated. It is nd. Sigma is the reaction probability, phi is the neutron flux, and t is the radiation time. After waiting 10 from radiation and disintegration, that is dt is equal to sigma phi d 1 minus lambda t into lambda t, or n is equal to m by m x na, where m is the mass of radiated sample, m is the molar mass of the substance, x is the frequency of radiated isotope, and n is the Avogadro number. That way we can calculate the, for a specific reaction, the variables commonly known as number of nuclei in the which is radiated can be calculated. However, as a rule, factors that capture cross the of the nuclei and neutron flux in the reactor is somewhere uncertain. The sensitivity is depend on the flux at the activating particle and the reaction probability or cross section of the reaction and the radiating time and the nucleides of life period. Meanwhile, the property of radiation emitted by the formed nuclei and efficiency to detect this radiation. In that way, we can able to analyze the material, and that process is known as neutron activation analysis. Is it clear? Thank you.